In the next section, we'll look at string matching using finite automata, or DFAs eventually, of different such things. If you've had some undergrad class in automata theory, some of the things will be familiar, but it's not often discussed as an application of all that theory. I think it's a nice way to motivate that. So just to see where people stand on this. I won't rely on this much. I could already make a prediction how this will pan out. Probably the 2/3 who do advanced computer science have seen at least part of this, and the other third might not have seen much of it. So it's the same old problem. I can't really rely on everyone knowing it. But in this case, I don't think it's repetition, so I'll just go through it. I knew there's a way. Okay, if I remember correctly, we had a few more people vote for the attendance code, 128. But most people have cast their vote. This is not so important, so many haven't heard about this. And then the others are split between, okay, I've heard this before, but I don't really remember so much. Plus a few others. So in this case, we don't really need to know any about this. It just makes connecting the dots a little nicer for those of you who know it. But you can follow the part that I present either way. For those who know it, the short solution for string matching really should be, we try to find the pattern somewhere in the text. That's to say, we try to represent the text as the pattern plus some string of arbitrary length before it and some other string of arbitrary length before and after the pattern and before the pattern. And because it's sigma star, both can be empty, so it's fine if the pattern occurs right at the beginning and so on. That's just a different way to phrase the problem. Now I've lost in this, for the moment, the restriction that we want to find the first occurrence of the pattern. That's a bit more tricky to express, but you can still try. But we won't have to worry about this. The automata theory or formal language theory part here would say, this is a regular expression or a regular language. It's recognized by a regular expression. And so that means we know that's basically automata or formal languages theory. There is a thing called deterministic finite automaton. I'll show you what these are. That recognizes this. And so we can feed the text through this in exactly n steps, as many steps as the text has characters. Not n times m or anything like that, right? Just n steps once we have the automaton. And that automaton should be able to decide if the text is of this form, which means it contains the pattern, or not. So that's good. A theoretician might say, okay, cool, that's all I need. But maybe not. There's a few things that are open. First of all, maybe you don't know all this stuff, then it doesn't help, but you can learn about it. More seriously, though, this would only tell us there exists a pattern, but it doesn't tell us where it is. It only exists, it says there's some occurrence of the pattern. It doesn't tell us where. And also, who knows, like this automaton, that's an existence. That just says there is some, but maybe it's absurdly big and it's just beyond practical. And both of these problems could be very real. Now, it turns out they both aren't really a problem, but you want to look inside the black box to see that that indeed is the case. So let's first go over what an automaton is. For us, we can basically think of it as a diagram like this. We have states. These are the circles. I just numbered them. They can have other names if it's convenient, but this doesn't matter. It's some set of states, and we will use the numbers because they have some meaning in our case, but that's up to us. And we also need an alphabet associated for such an automaton. That's the type of letters that can occur on these edges. We also need a start state, so that's usually just shown by a little arrow coming out of nowhere. That means you have to start in state 0 initially. There are these double line states. These are accepting states. That has a meaning in the formal language sense. For us, it will just mean, okay, we found a pattern. That's kind of the success moment. And then there's all these arcs, which tell you, if you're here and you see as the next character an A, you should follow that arc and go to state 1. Now, more formally, people often write this, instead of drawing this picture, you can specify the so-called transition function. And I'll always use delta for that. That's a function that maps from the states. So Q is the set of states. Sigma is the alphabet that we use. It maps from a pair of states and the next character that we read to a new state. So for example, here, the edge I just showed you, when we are in state 5 and we read an A, we go to state 1. Okay? So you can either give the automaton by specifying this transition function plus all the other information. You need to say what the start state is and what the alphabet is. The transition function you can give as a table, then it's kind of implicit. You can say the states. Okay, let me try to squeeze this here. We can have the states up here. And we can have the letters as the rows. And then you can try to fill that table. And I'm not going to do it because it's too many steps. I'll bore you to death. But the entry for 5 and A should be a 1. That's that entry here. Okay? So you can either give the table or you can give that drawing. We don't need to be overly formal on this. Now, there's one important bit that I didn't talk about yet, and that's the word deterministic. Deterministic means there shouldn't be any ambiguity or any chance. Now, where could there be ambiguity? If you look at the transition function, the way it's called a function means for every pair of states and symbol, there can be exactly one state, and also there has to be one. So if you draw the table, that's kind of obvious. But in the picture, you could have several outgoing arcs with the same letter, or there could be letters missing. So deterministic just means exactly one arc for each pair of a state and a character. Okay, so what does all of that have to do with string matching? What I'll promise you on this slide, and we'll come to how to get there, is that this automaton that's drawn here is capable of helping to recognize texts that contain this pattern P. Okay, first obvious thing to note, if you look at the pattern, you find the pattern here, A, B, A, B, A, C, A. If you just follow the edges that go left to right, you find the pattern again. So at least it occurs in some sense in the automaton. That's reassuring, right? The way this automaton works now is hopefully very intuitive. You initially start in the start state. You always are in one state. And then you just do what the arcs tell you to do by reading through the text. So you're initially in state 0. Then if you read through the text, the first thing you find is an A. So you're in state 0. You read an A that takes you to state 1. So I'm probably not going to be able to do this for all of the letters. Otherwise, we'll get in a very messy picture. I'll just draw it for one transition. Now we're in state 1, and we read another A. The arc there takes us back to state 1. And that's all that you do. Now, if you ever reach that state 7 while you're doing this, you found an occurrence. And that's kind of obvious because we just followed these green edges. The more interesting statement is that if you do not end up in state 7, then there's no match up to this point. And we'll get back to that. Let's complete the table just to finish this off. So we're in state 1 still. We read a B. That brings us to state 2. We're in state 2. We read an A this time. So I'm just going through the characters of the text, right? This is the text written down again. So from state 2, reading an A brings us to state 3. From state 3, reading a C, all the way back to 0. All right. 0 reading an A brings us to 1. 1 reading an A brings us back to 1. 1 reading a B advances us to 2. Now we see another A that brings us to 3. We've been there before, but this time we see a B, which gets us further to state 4. From 4, we read an A, gets us to 5. And then we read a C and then an A. So you get to 6 and then 7. And so that means ending with the current letter, with the one that we've just read, there's an occurrence of the pattern. So from here down to, well, the length of the pattern back, we have AB, AB, ACA. That's our pattern. OK? And for string matching, we would now return that we basically found a match starting at this position. So that's the connection between those two. And here's the same information without the messy drawings. Now, you could spell this out in code, and you find detailed code in the book if you want to look that up. Now, the code can't use these kind of diagrams, but it can use a transition function and variables. And so you maintain the current state. You read the next character. You take the transition table to tell you what the next state is that you go to. You just keep going like this, each time checking if you reach the final state. So the code for that is not hard. And each step just takes you, each letter of the text just means one lookup of the next state and potentially a check for the final state. That's very cheap, right? So let's also write that down. We read at most each text character once. And you should compare this to the brute force method, which in the worst case needed n times m. Right? If m is a few hundreds of thousands of characters long, it's quite a reduction. Now, of course, this all hinges on someone telling you what this automaton is. And let me also tell you, if you just took the arcs that go left to right and don't pay attention to those going back, then you can miss occurrences. So you can't always just jump back to 0, for example. So what we're still missing is a way to build that automaton. But if we have it, we have a good string matching algorithm. Now, to build our way towards this, let's first understand the automaton more and then worry about how to compute it efficiently. And the main insight is to give the states a specific meaning. And once you internalize that, much of the rest falls kind of into place. So that's an important bit to pay close attention to. The intuition is that if you're in state Q, that means you've read some part of the text, fine. So you may have seen the text up to this point, and it may continue. But at this point, you've seen a certain part of the pattern, a certain prefix of the pattern. So maybe the pattern can look like this. And you've seen up to here a certain prefix of the pattern, in the sense that if this is P and this is the text, then these characters are all matches, so they're all the same. Okay, you always have seen a prefix of the pattern if the prefix can be empty, right? So this is not saying anything. You can always find a Q so that this is true if you set Q to 0, for example. But the point here is that it has to be the longest such. So there's no way to put P further to the left and also get matches all the way across. So this means somewhere along the way here you have a mismatch. You have a character that doesn't match. If you're in state Q, it means the length of this thing is Q. And whenever you shift the pattern further inwards to the text, giving you more matched characters, something goes wrong at some point. One of the characters is mismatched. Okay, so we've seen the prefix of the pattern, and that's the longest we've seen so far. Okay. Now, you may wonder, if we take a step back, how is it even possible to have a single automaton that works for all texts? Now, we still have to read the text, but how can it be that we can find occurrences in the text if all we build the automaton on is the pattern? And the reason to see that that's enough information, that all the information you need is this prefix of the pattern you've seen so far, is the next step, read the next character and see what can happen. So if we're in a certain state Q and we now read a character C from the text, we don't know what that is. The text could be anything. So one letter C comes. So there's two options. It could be the next character of the pattern. Then we just go to the next arc. So if we're in this state, then we've seen the first 3 characters of P and not more. If we now see a B, then we've seen now the first 4 characters of P, and that's the easy case. If we have a non-match, so there's not the right character coming, what can we say? Well, we've seen so much of the text. Let me draw this again to not clutter it up too much. So the text may continue. In particular, it continues one further letter with C. And we're in this state we've seen up to here. Let me draw it so I can draw the green things in between. This is the pattern. And then we had matches up to that position, but then a mismatch with C. And this here is the first Q characters. That's the situation we're in. And now the argument is, all we need to know is in this prefix of P. It doesn't matter what the text looks like before that occurrence. So everything that's before that occurrence is irrelevant from the text. And the reason for that is that we picked the longest prefix. If C is a mismatch, then we have to shift P further to the right to get a match again. If there was a way to shift P to the left, then chopping off that last character would give us a longer than the longest prefix, and that's a contradiction. So what we can find is some Q prime, as shown in this picture here. All right, let me draw it again, so that you can shift the pattern a bit further. And now you can get alignment up to this point of all the characters here, including the C. And we already know this Q prime must be at least one shorter than Q. It must be strictly less. Otherwise, we would get a contradiction to this longest prefix from previously. So that's why such an automaton is even possible. All you need to do the next step to maintain this invariant, that you're in a state that stores what's the longest bit of the pattern that I've seen so far in the text ending here. All you need for that is in that prefix itself. So the automaton can work for any text. Now, this kind of argument is also the correctness proof of the string matching procedure. That's what I alluded to earlier when I said, when we were discussing this example, the easy bit is that when you reach the state 7, the accepting state, that you found a pattern occurrence because you just walked along this path. The more tricky bit is to argue that if you're not here, then you have not found one. So what you would have to do is prove by induction that this invariant is always maintained. And because it's the longest prefix of P that we've seen up to this point, if all the way through the text you never reach up to state M, the length of the pattern, then you've never seen the entire pattern. This part is a little less intuitive to explain. I think you have to go through this invariant. Is there a question? A letter B?
In the end, after E.
Are you in this example?
Yes.
So a letter B at the end of the text or at the end of the pattern?
Text.
So another B at the end here?
Yes.
So as you see in the picture, the way the automaton is drawn here, it would just stay in that state 7 forever. So what this arc with sigma means is it stays there no matter what comes. We don't really use the automaton like this because the first time we reach that state, we will just immediately return. You could modify the automaton to keep going so that you can keep reading through the text. That's a small modification. Now, so in this example, it means whatever comes, you will always stay in state 7. I'm not sure if that is your actual question. In this, that's kind of a boring answer. I think you'll look at this in one of the tutorial problems as well. You can just extend the construction for the automaton to the last state, and then you get the matches, the edges that you would need for the mismatching characters there. So you can extend the automaton so that it keeps reading, and it just flies by this accepting state whenever there's an occurrence. That's maybe worth noting down. We might I comment on this in a later unit on the parallel problems. But because we discussed it anyways, let me write it down briefly. keep finding other occurrences. So what this is getting at is the DFA can find all occurrences. In essentially the same time. It can just tell you once it found one. I think the book has detailed code for that part, finding all occurrences. We'll at least get to it in the context of the KMP algorithm. If you're very keen, maybe ping me on CampusWire. The changes are not too hard, but maybe if you're seeing it the first time, that's not quite true.